Hello, Mr. Price here, and this is the 6th video of the January 2007 Mechanics 2 paper, and this is a centre of mass and a little bit of moments question. Let's have a look at it. So we have our uniform lamina, which has a weight of 30 newtons, and it's made up of a rectangle and a triangle. Okay. And we're being asked to find the centre of mass of this lamina using AE and AB. So basically this corner here is our datum position. Okay, so we're going to draw a fairly large diagram here. Okay, because I like to put on various bits of information here. Okay, so here's our lamina, and this is our datum position here. Now, to get the centre of mass, we're going to need the centre of mass of our two shapes here. Okay, so this is 9 centimetres. This bit is this is metres, is it, or centimetres? Centimetres, 3 centimetres. This bit's 12 centimetres. And that's all we're given. Okay, so this one is fairly straightforward. The centre of mass here, it's a rectangle, so using symmetry, it's 1.5 metres away from the datum position, and then 4.5 centimetres away from the datum position, because it's perfectly in the centre. Okay, and then for this one, we're going to need to get the centre of mass of this triangle. Okay, there's no symmetry here from what I can see. Note, it's a scaling triangle, so no lines of symmetry. So we're going to have to do this one the old-fashioned way. And to do this, we need the coordinates of our vertices of the triangle. So this is, excuse me, this is 3 centimetres away. So this point is 3, 0. Okay, this one is 3, 9. And then this one is 15, 9. Okay, so x bar of the triangle is 3 plus 3 plus 15 all over 3, which gives us 7. And y bar triangle is 0 plus 9 plus 9 all over 3, and that gives us 6. So this has the coordinates 7, 6 from the datum position. Okay, so we now want to find the overall centres of mass, and to do this we're going to need the area of shape 1 and the area of shape 2, because it's a weighted mean, and we're going to take the area to be effectively its weight of each individual object. Okay, because we don't know the density of the object. So area 1 is 9 times 3, which is 27 centimetres squared, and area 2 is 12 times 9 all over 2, 6 times 9, 54 centimetres squared. Okay, so x bar is the area of shape 1, 27, which is 1.5 metres away from the datum position in the horizontal plane, plus the area of shape 2, 54, and that is 7 from the datum position, all divided by 27 plus 54, which is 81, Working that out, we get 5.16 recurring centimetres. And then for y bar, we have 27 lots of 4.5 plus 54 lots of 6 all over 81, and this is 5.5 centimetres. Okay, and that is part 1 done. Fairly straightforward, 8 marks there. Okay, for part 2, our laminate is freely suspended from the hinge B, and we want to calculate the angle AB makes with the vertical. Okay, so I'm going to do a quick sketch here. So here's my point B, and then we've got our line here, line here, line here. Okay, it looks something like this. Doesn't have to be super neat. Okay, and our centre of mass is going to be directly below point B. It's going to hang through our centres of mass. Okay, so what information do we know? Now we know this distance is 5.16 away from that edge. Okay, and it's 5.5 away from this edge. So therefore, if we draw this triangle here, okay, we've got A, B and C in case you can't see. So A, B and C. So A will be 9, take away 5.5. So that's going to be 3.5. And then this is 5.16. Recurring. And we want to know this angle here. Okay, so using tan theta equals 5.16 recurring over 3.5. Using inverse tan, you get an angle of 55.9 degrees to the vertical. And that is part 2 done. Okay, finally for part 3. The laminate is now held in position such that BD is horizontal, so it's in our correct orientation, like this. And this string is attached at the point D, which is fixed 15 centimeters directly above the hinge at B. Okay, and we want to calculate the tension in the string. So, another quick diagram here. So, we have a tension here at an angle, and then we have the weight, which we were told subtly at the very start of the question as 30 newtons. Okay, and effectively there's a pivot here on the hinge. Okay, now we don't know this angle yet, but we can calculate it. So we were told that the string is attached to D and is fixed 15 centimeters directly above the hinge. Okay, so basically there's a string that goes along, and here's hinge B, which we know is 15 centimeters away from the edge. Okay, and that is 15 centimeters. So you've got a isosceles triangle. So this angle here must be 45 degrees. Okay, so now we just take moments about B. Because this is an equilibrium, so forces must be equal, and so must the turning points. Okay, we can't use forces up or down because we don't know what this force here is. Okay, but if we take moments about this position, this turning force is irrelevant here. That force does nothing to do for the turning force. So moments at B. So we already know this force is going vertically downwards. So the horizontal distance was y bar, which is 5.16, sorry. Okay, and this distance is 15. So we can say that clockwise moments equals anti-clockwise moments. So if the pivot's here, this one's causing a clockwise moment. So 30 lots of 5.16 will be equal to t sine or cosine 45. Doesn't really matter that much, but we want this force, so technically it is sine 45. Okay, so if we're resolving vertically, we want the horizontal distance to the pivot point, which is 15. So solving that, you should find a tension of 14.6 newtons. And that is question 6 finished.